Very good evening to everyone. Welcome to the third problem solving session for the course Geosynthetics and Reinforced Soil Structures. I apologize, I had some important commitments yesterday, so we did not have this meeting at our usual time. But last week, I'll just share my screen. So this is lecture number 9. We are talking about lecture number 9, 10, and 11. We have discussed about reinforced soil walls, mostly about the construction methodology. And we have also touched about a brief about the design of reinforced soil walls. So need for returning walls, types of retaining walls. I assume you are already aware about the basics of soil mechanics. Uh, Soil has limited strength, so it cannot stand at steep angles. And whenever we have a structure where we require steep angles, you need to provide some support. And if the angle of the slope is very high, about 90 degrees, we call it a wall. If it's low, say about 30-45 degree, we call it a slope. So we are specifically talking about walls here. Reinforced slope is another topic which is not kind of covered here, but the principle remains the same. Then we have types of retaining walls. We have rigid walls, which are made of RCC. We have flexible walls. Some types were given. History of the uh, retaining walls. Here is some photo of a secant wall at the bottom and some anchored uh, soil nails at the top. So anchored means you have to actually pre-stress this. So whenever you pre-stress this, some external force is applied which stabilizes the soil. So that's why you pre-stress. So here you can see the pre-stress mechanism. So you can assume that if there is a wall and you are pre-stressing one of the anchors or soil nails, then say you are pre-stressing it to 500 kilonewtons. So that means an external 500 kilonewton load is being applied, which stabilizes which reduces the deformations and stabilizes the wall. So you can see this is very, very common in diaphragm walls. Wherever you want to have construction of a building with deep basements, then you need to construct this diaphragm wall because these buildings are actually in a very, very congested area. So one way is if you had infinite amount of area, you don't even need to construct these vertical walls. You could just have a stable slope at the angle of repose of the soil. But since the area is restricted, you have to have a vertical walls. That's why you require these methods. Then basic principle of reinforced soil. This has been already been discussed. Uh, General outline. You have a backfill soil. You have a reinforced soil block and leveling pad. Again, the history, uh, type of wall facing. You can have full panel, segmented, or modular box, block, or geotextile, or wrapped geotextile. Different type of reinforcement. Geogrids are the geogrids and geotextile are the most common. So whenever you go at a flyover in your city, you will definitely see one of these being applied in layers while constructing the approach road for the flyover. These are the costs, uh, comparison, different types, some examples. Moving on to lecture number 10. We had some amazing photographs from the professor of the sites, which can give you a great idea of uh, just hold on a second. I have a very important call to take. I'll get back. Just give me a minute. I apologize. It was a call from my professor, so I cannot skip that. I hope you guys realize that. Yeah, so back to what we were saying, different types of RE walls built in India. You have different facings. Some of them are flexible, some of them are not. Uh, so this is relevant because sometimes you have allowable limits for the deformation of the vertical walls. So that allowable limits depend on what kind of facing do you have. If you have rigid facings, the allowable limit for the vertical deformation would be less. So you have to calculate what is, sorry, the not the vertical displacement, the horizontal displacement. So if you want to uh, set the allowable limit, you should know what kind of facing for the RE wall is provided. And this is a full panel, again, full panel, photo of the leveling pad. This is GeoGrid, modular blocks, again, modular blocks, which is a flexible, and you can see this differential settlement. So probably they knew that this differential settlement would occur. That's why they used modular blocks. If they would have used single panels, they would have cracked pretty early and would have probably have more cracks. And so I'll just brush up very quickly. These are segments, the connection between segments, the casting of reinforcements, geotextile to prevent fines, bulging, strips, gabion walls. This is river training works and just a bit of construction methodology, some examples. Here you see the analysis. This is done, I think, using a limit equilibrium method, which I have also showed you in the first class. And finally, we are at lecture 11. Some British standard codes. I recommend you all reading this code specifically. Then this itself is a book. It's not a code. I would say it's a book. It's the best book that for anyone learning reinforced soil retaining walls. So you can definitely go through that. It's very well explained to the point. It's not very elaborative, so you'll get an understanding. And then a difference. What are the gradations? suitability of the backfill soils. Then you have lateral earth pressure theory, which I believe most of you have already studied in your undergraduate. And if not, then we'll just, I'm sure that after the lectures you would have understand. This is the Rankine lateral earth pressure theory. We have calculated the total horizontal force at the moment generated by the this force. Simple, taking the area and centroid of the area, you'll get the distance and the total load. And this is if you have a slope fill, how does it vary? Coulomb's equations takes the uh, roughness of the wall also into account. And then you have the design loads. You have internal stability, external stability. Internal stability is the slope stability. External stability involves all this. This has been explained. I hope you understand. We'll have a question today on this, where we have to calculate what is the bearing capacity for this whole rigid block. So it's just like a footing with the width of this. So you have to calculate what is the factor of safety for this whole sliding block. We have not discussed still how to calculate the internal stability. That's why we don't have questions in this session, but in the next sessions, we'll discuss about internal stability. But I assume that most of you are aware of bearing capacity theory. If somebody is not aware, they can ask. I'll just briefly explain what is the how you can calculate the bearing capacity. And you just have to use your undergraduate bearing capacity method, and then you can find out the factor of safety for global failure. So this is an external failure mechanism. So you have to make sure that the weight of this whole block, rigid block, does not cause any bearing capacity failure. And then different load combinations, and you need to find out this question also. I don't know if it was discussed in the class. I did not attend the class, so but you can, I think, find the answer to this question. To I think we'll discuss it here also in the class also. But otherwise, you can just look at the British code for the answer. So this is it. Now let's come back to the questions. So these are the questions for today's session. First question, very simple. I think most of you would answer. Second is an MCQ. Third is also an MCQ. Fourth is the question where you have to calculate the factor of safety for the external stability for reinforced soil wall. I'm not calling it reinforced earth wall because it's a proprietary term. It's not copyrighted by a company. So the correct word is reinforced soil wall. So you have a lot of factors given. You need to see several codes. Just see the code for bearing capacity for shallow foundations. I think it's IS 6401 if I'm not wrong. Let me just check. Oh no, it's not. 6403. Yeah, so IS 6403. You need to calculate the, here it's written that use Mayer-Hoff theory, but you can use whatever theory you like, possibly the one mentioned in the IS code, which is basically the basics theory. But you can use Mayer-Hoff's theory to calculate this, or the basic theory. And You have to, I think this is pretty straightforward if you are aware of the bearing capacity theory. And the last question is similar to what was given before, but I've still repeated the question. And this is also kind of straightforward. You just have to repeat the same step at 2, 4, and 8 meters. So I think question number 4 and 5 are going to take some time. Otherwise, 1, 2, 3 are pretty straightforward. So I think we will discuss. You take 1 hour. We'll discuss the solutions at 8:20. I have not yet uploaded the solutions to the link. Questions have been uploaded. Please see the link in the chat box to get these questions. And we can discuss at 8:20. So if anybody has any question, they can ask. Otherwise, I'll see you at 8. Or they can also ask question in between if anybody has any doubt. Otherwise, everyone else can proceed. Thanks. I hope you have been able to solve most of the questions. We'll just swiftly discuss the solutions. The first question, first part I've already discussed. It's pretty straightforward. The equation is this, and you'll get the answer. In the second part, you multiply by a factor of 1.5, which is the factor of safety. So, and in the third part, there is a value of required geotextile modulus. And you multiply it by 10. It's because you are actually limiting the strain value to 0.1%. That is why you are actually dividing it by the strain value in order to get the value of 10. So allowable or maximum tension divided by the allowable strain will give you the required modulus. Next question is, which one of the following geosynthetics can be used as a reinforcement in the construction of reinforced soil retaining walls? The first obvious answer is GeoGrid, but it's not there. Non-woven geotextile is generally used for drainage and filtration purposes. So you generally do not use the non-woven geotextile for reinforcement. Geonet is again for in-plane drainage. Geomembrane is acts as a barrier. So the answer is woven geotextiles. So woven geotextiles and geogrids are the most common form of reinforcement for reinforced soil walls. And vertical spacing of reinforcement layers for soil walls is 0.1 to 1 meters. Uh, this is specifically for soil walls. If you are using it for uh, improving foundations, then the spacing may increase. So this is specifically for soil walls. Third question was regarding the safe bearing capacity. You have to use the theory for a shallow foundation only. Most of the values were already given. The height of the height of the wall, then the width, and because of some eccentricity, you have effective width. Border table was not encountered. Based on all of this, you get the total base pressure. This is the required safe pressure, and then how you generally calculate the value of soil properties is you calculate the average SPT value, which is 27, and based on that you get a correlation and get a phi dash of 32 degrees. Unit weight is mentioned, embedment depth is mentioned. You can use any bearing capacity factor. You can always refer to IS 6403 to get these values. And since you might know that below 30 degrees and after 35 degrees, you have general shear failure and local shear failure. So value is 32 degrees. So it will be in the category of intermediate shear. So you have to interpolate the values. Depth, shape, and inclination factor. Shape and inclination factors won't be there. Depth factor you have to calculate, and the factor of safety against your bearing capacity failure has to be taken as 1.4. This is the equation. You put in the values. I think only the depth factor here is 1.037. Most of the other factors are equal to 1 only. And you get this value. You divide it by factor of safety, you get this, and your required was this. So it's safe in external stability. Remember, there are many more checks. You have internal stability also, which we'll discuss in further sessions. You have external stability for overturning, for sliding. So we have not checked that. We have particularly checked it for bearing. And since usually the width is very large, the uh, width depends on the length of the reinforcement layers. So since it's usually very large, the bearing capacity is generally not a problem in reinforced soil walls. Next question was again a geotextile reinforced soil retaining wall. So this was a wrap around geotextile reinforced soil retaining wall. It was not explicitly mentioned in the question, but if you see, there is a lap length asked. So whenever you wrap around a geotextile, you have to provide some lap length so that this slippage does not occur. So that's why. So this is particularly for wrap around geotextile reinforced soil retaining wall. The parameters were mentioned. You have to calculate the active earth coefficient to calculate what is the horizontal force. So how much uh, tension has to be required, is required for the reinforcement. You can use this or 1 minus sine phi divided by 1 plus sine phi. And then you actually calculate the value of spacing. This has been discussed in the lecture. So basically, this is the vertical load is your gamma z into b, gamma b into z. You multiply it by Ka, so you get the value of the active earth pressure. You multiply it by the spacing, you get the active earth pressure acting on a single uh, geotextile layer, and the allowable value divided by the factor of safety gives you the resisting force. So equating the resisting force with the driving force, you get this equation. Rearrange and find out the value of SV. So you do it at different depths. So you get a value for at a different depths of what is the length of the reinforcement required. Now, oh, sorry, spacing of the geotextile layers. I'm sorry. Second part is the length of the geotextile layers. So here it contains two parts, LE plus LR. So if I just show you, say this is the geotextile wraparound geotextile I was talking about. This LL is the lap length. You wrap it around and you have to provide some lap length. And this is your Rankine failure wedge. So the geotextile length inside the wedge is known as LR, and the part outside the wedge is known as LE. So the total length is going to be LE plus LR and plus lap length also. So here LE plus LR is given. LR value you can find out from the geometry only. This will come out to be this varies with Z. And then LE value, uh, again, simple, you have to calculate what is the force acting, what is the friction. So here phi, you have to use interface friction angle, which is taken as same as the soil internal friction angle. Sometimes it can be taken as lesser value, say 2/3 of the value, which was as seen in the first example. So in this example, it has been taken as equal to phi b, and based on that, you calculate the different at 2 meters, you need this. And as you go down, you read lesser reinforcement length. And then lap length, which is specifically for a wrap around. Uh, this again is based on a similar principle. The details of the derivation of these equations we'll discuss in later classes, but just to get a brief outline, uh, just because we don't have a lot of numericals in these initial weeks, but later on as we move, you'll get used to these equations, and mostly are based on very simple phenomena that by the friction angle, be it the soil friction angle, or if you're talking about an interface friction angle. So tan of that interface friction angle will give you the resisting force, and the driving force is usually the active earth pressure acting due to the wall, self weight of the wall or the surcharge. So you just have to equate those to get these values. Uh, it's very straightforward, and you don't even need to memorize this. You can derive it like in 15-20 seconds. So this is it. If anybody has any questions, they can ask. So I don't think so. We have any questions. Someone had asked that if you have link to previous sessions. Uh, I think the every week on I think Thursday, link is shared in which feedback is asked, and also a link for the previous session is shared, and it's all is uploaded on a YouTube channel. So just you can view that YouTube channel on the uh, YouTube app, and as we move on, the videos will be automatically updated, so you don't have to follow that link always. And same is with the Google Drive link. All the files, all the questions and their solutions are uploaded on a single link. So just click it and save it in your drive. So you don't have to reach out to the link every time, so that you can easily access that. So I think this is it for this week. From next week onwards, we are going to have numerical problems and some example problems we'll discuss, which are based on the design, or more on the design part of reinforced soil walls. So a very good night to everyone, and I'll see you next week on Monday from 7 to 9 p.m. Thank you. Take care.
Good evening, Pranjal.
Oh,
This is Professor
hi, sir. I didn't
Rajagopal.
see that. Good evening,
Yeah,
sir.
actually, I'm surprised that only 2 or 3 students are here. But anyway, it is. I just want to inform the students that some numerical example problems are also uploaded um, as part of the lecture materials, and they can download them. And I see that you have also solved some example problems.
Yes, sir.
Um, so I think that should more or less help the students in understanding the topics. And
Mm.
it's actually, I hope the course is going well, but I don't see any students asking any questions in the forum. I keep checking the forum at least twice a day, but I don't get any questions.
Sir, I think in the later part, when more numericals and example problems.
Yeah, yeah, yeah. Okay, so thank you, Pranjal. You're
Thank you,
taking a lot
sir.
of time and efforts. Okay. So
Thank you,
good
sir.
night to all the students.
Good night,
Okay.
sir.
Yeah.
Thank you.
Good night. Good night.
Bye.